Welcome all. In this lecture, we will be discussing about the braking of traction motors. Following methods are adopted for the braking of electric motors: mechanical braking, hydraulic braking, electric braking. But in this lecture, we will be emphasizing our focus only on the electric braking. Further, electric braking can be classified into three: dynamic braking, plugging braking, and regenerative braking. Before discussing about the dynamic braking, plugging braking, and regenerative braking, we need to discuss about the operating principle of induction motor and its torque slip characteristics. Let us discuss the principle of operation of three-phase induction motor. In this diagram, consider this section as the stator part of the induction motor and this section as the rotor part of the induction motor, where these are the conductors on rotor part and these are the conductors on the stator part. When a three-phase supply is provided to the stator part of induction motor, it generates a rotating magnetic field. Which is rotating at a speed of ns, where this ns is equal to 120 f by p, where p is the number of poles and f is the frequency of the supply. Let us assume that this magnetic field is rotating in a direction. Let us say the magnetic field is rotating in the clockwise direction with the speed ns, where this ns is equal to 120 f by p. When this rotating magnetic field rotates in this stator part, it cuts the stationary rotor conductors and hence it cuts the rotor conductor, which causes a change in magnetic field around this conductor, and as per the law of electromagnetic induction, an EMF will be induced in the rotor conductors. So an EMF will be induced in rotor Now this EMF will cause currents to flow into the rotor conductors. So rotor current will start flowing, and when the rotor current starts flowing into the rotor, they will create their own magnetic field, and hence a rotor magnetic field will set up. And now the motor has two magnetic fields, one rotating into the rotor section, stator section with a speed of ns, the other is the field of rotor magnetic field. Now this rotor magnetic field will try to catch this stator magnetic field, and hence the rotor will start experiencing, I would rather write rotor will try to align itself in the direction of stator magnetic field, and as the stator magnetic field is rotating, the rotor will start rotating. Rotor will rotate, and let us say the speed of the rotor is nr. Now let us discuss what will happen if we cut off the three-phase supply on a rotating magnetic field, and instead of three-phase supply we provide DC supply on it. Rotor is rotating say in the direction of the stator magnetic field, previous stator magnetic field, but now we have cut off the three-phase supply and we are providing a DC supply. When we provide a DC supply, it will not produce a rotating magnetic field, instead it will produce a stationary magnetic field. Now the rotor is rotating, but the magnetic field produced by the stator is stationary. This stationary magnetic field will cut the rotor conductors, and hence an EMF will be induced into the rotor again. This rotor EMF will cause rotor currents to flow into it. Now this rotor current will produce its own magnetic field, but this magnetic field will again try to align itself in the direction of stator magnetic field. But this time stator magnetic field is not rotating, it is stationary. Hence the rotor will try to come to the stop position or the halt position to align itself into the direction of stator magnetic field, and hence the rotor will not rotate, instead it will try to stop. This method of braking of electric motor is known as the dynamic braking. We term it as dynamic braking. So what happens in dynamic braking? On a moving motor, we cut off the three-phase supply, and instead of three-phase supply we provide a DC supply. This DC supply will produce a stationary magnetic field. This stationary magnetic field will cut the rotor conductors, and EMF will be induced into the rotor conductors. Further, rotor currents will start flowing. These rotor currents will produce their own magnetic field, which will be rotor magnetic field. Now this rotor magnetic field will try to align itself in the direction of stator magnetic field. As the stator magnetic field is stationary, the rotor will not rotate and it will come to the stop position. Hence the motor will come to the stop position. This is the dynamic braking. Let us now discuss the plugging braking. As we have already discussed, a three-phase supply will produce a rotating magnetic field, where the direction of rotation depends upon the phase sequence. Suppose we are providing a phase sequence of R by B and it is causing the motor to rotate into the clockwise direction. As we already know, if we change the phase sequence of the motor, let us assume the phase sequence now is RBY. If we change the phase sequence of the motor will produce torque in the opposite direction. That means the rotor will now try to move into the anti-clockwise direction. And this torque will first try to bring the motor to the halt position and then will cause it to rotate into the reverse direction. But we will cut off the supply of the motor as soon as the rotor speed becomes 0. Hence the motor will stop. This is called the plugging braking. So in plugging, we reverse the phase sequence of the supply provided to the stator winding. Let us discuss regenerative braking. We know that the torque produced by induction motor is directly dependent on the slip of the induction motor. To reduce the speed of the induction motor, that is while braking, we need to produce the torque in the opposite direction. That means the T should be negative. For T to be negative, S should also be negative. So we need to produce a slip with negative S. When this S is negative, it is said the motor is acting as a generator or acting in the generating region. That is, now the motor will be acting as a generator. Now let us see how the slip can be negative. We know that slip is equal to Ns minus Nr by Ns. So the only possible way to make slip negative is we should produce a slip, we should produce Ns which is less than the current speed of the induction motor. That is, Ns is less than Nr. That is, if we create a condition where Ns is less than Nr, only in that case S will become negative. Let us now see the factors on which the synchronous speed depends. We know that Ns is equal to 120 F by P. That means to reduce the speed, we need to decrease the frequency. So by using variable frequency converters, we can produce frequencies lower than the supply frequency. That is, F1 will be less than F. Now this lower frequency will produce a synchronous speed less than the previous synchronous speed, ns1 will be less than ns, and hence when ns1 is less than ns, and also if the new ns1 is less than nsr, then we would be able to produce s with negative slip. Hence the torque produced by the motor will now be negative and it will start retarding, that is its speed will decrease. Let us understand this further with the help of a torque slip characteristic. This is the torque slip characteristic of the induction motor, where TL is the load torque and this blue curve represents the variation of torque with the speed of induction motor. To supply this load torque, motor will be running at a speed of say nr, and if we want to reduce the rotor speed, we need to reduce this ns by varying the frequency. By reducing the frequency, we will be able to produce the synchronous speed which is less than the ns, present ns. Say the new torque slip curve at the frequency f1 is given by this yellow curve. This is the torque slip curve at frequency f1. This is the torque slip curve at the frequency f. Now, to deliver mechanical power at this torque, the motor needs to attain a speed of this nr1, and in this way the induction motor will retard to a new value nr1, where this is new synchronous speed and this will be the new rotor speed of the induction motor. We can notice during the retarding period, during this period, the slip is negative because nr is greater than ns1. If the slip is negative, that means the motor will now be acting as a generator, and it means this, that motor will not be drawing any electrical power from the supply. Instead, it will be delivering back the power to the mains. Hence, in this way, in regenerative braking, some of the power stored which was stored as inertia of the motor or the locomotive will be returned back to the supply mains using the regenerative braking, and hence the regenerative braking is one of the best and efficient ways of braking in electric locomotives. That's it for this lecture. In the next lecture, we will be discussing the amount of energy delivered back during the regenerative braking.